Now let's talk about texture streaming, a feature that has become increasingly mature in recent versions of Unity. From a memory management perspective, texture streaming is now considered one of the most practical mobile optimization tools. First, let's revisit the basics. Earlier, we discussed MIP maps. Take a 1024 by 1024 texture as an example. When MIP maps are enabled, the engine generates multiple resolution layers, 1024, 512, 256, and so on. The total memory footprint is roughly 1 and 1/3 of the base level. When rendering with MIP maps enabled, the GPU automatically selects the appropriate texture level based on two factors: how much screen space the texture occupies, the relative texel density in the scene. This mechanism improves bandwidth efficiency, because the GPU doesn't need to fetch data from distant memory regions unnecessarily. That's one of the key advantages of MIP map-based rendering. But let's switch our perspective. From a memory optimization standpoint, an important question emerges. Do we really need to keep all MIP levels in memory? In many cases, the answer is no. During actual rendering, only a subset of MIP levels is actively used. For example, textures closer to the camera may use higher resolution MIP levels, while distant objects use lower resolution ones. This observation led to a natural idea. Can we safely discard unused MIP layers? Earlier Unity versions provided a rather aggressive approach. The texture quality setting allowed developers to globally reduce texture detail. For example, setting texture quality to 1/2 or 1/4 would forcibly remove the highest resolution MIP layer. However, this approach had a clear downside. It could introduce excessive blurring and negatively affect visual quality. And importantly, it lacked flexibility. Modern Unity versions replace this mechanism with a more sophisticated solution: texture streaming. Texture streaming allows the engine to dynamically manage MIP level residency. The system can intelligently discard high memory MIP layers based on runtime budget constraints. Here, we use a consistent definition. When we say lower MIP level, we are referring to the highest resolution layer, usually called MIP level 0. Now let's talk about prerequisites for using texture streaming. There are three main conditions. First, MIP map must be enabled. Texture streaming only works on textures that support MIP hierarchy. In newer Unity versions, MIP-related settings have been reorganized. The previous separate options, generate MIP map streaming, MIP map, have been merged. Now, enabling MIP streaming requires MIP map generation to be turned on first. When configuring streaming textures, you will also notice a priority parameter. Higher priority textures are less likely to have their MIP levels discarded. We'll explain its practical meaning later. Second, global streaming settings must be enabled. Inside player settings, quality, texture streaming, you need to activate the streaming system. In some engine versions, simply checking the setting in the editor may not guarantee runtime activation. For production stability, we recommend enabling it programmatically through API. Once enabled, several important parameters appear. The first is Add All Cameras. By default, this option is enabled. It means all camera rendering textures are included in the streaming calculation. If disabled, only cameras with a streaming controller component will participate. Next is Memory Budget. This is one of the most critical parameters. When runtime texture memory exceeds the budget, the engine will automatically discard lower priority MIP layers. It's important to understand something here. This budget is not only applied to streaming-enabled textures, it applies to total texture memory usage. For example, if non-streaming textures already occupy 5 and 12 megabytes, then loading a new streaming texture may immediately trigger MIP eviction due to budget pressure. Another parameter is max level reduction. This controls how many MIP levels a texture is allowed to discard. For example, if max level reduction is set to 2, even if memory pressure is high, the system will not remove MIP level 0 or level 1. Only deeper levels may be removed. Texture streaming also works closely with asynchronous loading pipelines. The engine first asynchronously loads the minimum required MIP level. For example, the level defined by max level reduction. This allows objects to appear visually faster. Later, if memory budget allows, higher detail MIP layers will gradually load. In gameplay, this may create a visual effect where textures appear slightly blurred at first and then gradually become sharper. That's expected behavior. Another prerequisite is asynchronous upload pipeline support. This requires assets to be packaged using LZ4 compression. Now let's talk about practical configuration. For mobile projects, we generally recommend setting memory budget between 200 and 256 megabytes. But this does not mean texture memory will never exceed that value. Instead, it means when memory pressure occurs, the engine will preferentially unload lower priority MIP layers. In other words, this feature becomes effective only when runtime texture memory exceeds the budget threshold. So choosing a reasonable budget value is critical. It must match your hardware segmentation strategy. The second important parameter is max level reduction. This parameter balances memory usage and visual fidelity. There are also additional APIs worth mentioning. For example, texture.streaming texture discard unused MIPs. By default, this value is false. This means MIP eviction happens only when new textures are loaded, memory budget is exceeded. It is a passive mechanism. This explains a common feedback we receive. Some teams tell us, we enabled texture streaming, but camera zooming doesn't seem to change texture sharpness. The reason is simple. The system was waiting for memory pressure conditions before triggering eviction. If you set this parameter to true, MIP evaluation may occur every frame, but this introduces a trade-off. On low-end CPUs, texture streaming itself may become a performance cost. In some extremely low-tier devices, continuous streaming evaluation can consume 1 to 2 milliseconds per frame. In such cases, optimization becomes counterproductive. For very low-end hardware, sometimes a more aggressive strategy is better. That means using smaller textures directly and simplifying asset design. For those devices, a hard cutoff strategy may actually be more efficient. In summary, texture streaming works best on medium to high-end mobile devices. The key is not maximizing compression, it is balancing memory residency, loading behavior, rendering fidelity, CPU overhead.